Hi everyone. This is my lecture on inverse problems, and I will only go halfway through. The real point is to introduce you to the idea of an inverse problem and to also introduce a mathematical model for an object that is exchanging heat with its surroundings. Here's a problem set up. A beer was inside of a refrigerator, and you took it out and put it on your table. So we'll assume that the beer was thermally equilibrated when it was in the refrigerator, and thus it started off at temperature T0, which is equal to the temperature inside the refrigerator. And indoors, the air temperature is TA, and it's hotter than inside the refrigerator. And so the physics that's going to happen here is heat is going to travel from the indoor air and transfer into the beer and warm it up. So the temperature of the beer, T, is going to be a function of time, and it's going to warm from its initial temperature T0 up to the air temperature TA dynamically. And note that I did not write this T of x comma T, where x is a spatial variable, so we're neglecting spatial gradients in the temperature and assuming that the temperature of the beer is spatially homogeneous. It's an approximation for sure. So we could develop a mathematical model for the dynamics of the temperature of the beer T by drawing a control volume around the beer. Chemical engineers should be used to this, and keeping track of the energy that goes in and out of the control volume. So we'll write an energy balance. Newton's law of cooling specifies that the flux of energy across this boundary is proportional to the difference in temperature between the indoor air and the beer. So this here is the thermodynamic driving force for heat transfer from the air to the beer. So here we're prescribing the rate of change of the temperature of the beer, and it's proportional to this thermodynamic driving force. But three parameters are involved in this. So one is the thermal capacity of the beer. That's how much energy it takes to raise this glass of beer by 1 unit temperature. A, the area across which heat transfer occurs. And H, the heat transfer coefficient, which is the amount of energy per time that transfers across this boundary per unit area per temperature gradient between the beer and the air. So this first order differential equation that models the evolution of T of T is subject to initial condition, where at time T0, we're going to let this be the time we took the beer out of the refrigerator. The temperature of the beer is T0, the same as the temperature of the fridge. Really, the dynamics only depend on this time constant tau, which is the ratio of C to HA. So there's only really one true parameter, and that's the time constant tau of the beer. So it's characteristic of both the beer, the shape of the glass, and the velocity of air across it. So if you blew a fan here, the heat transfer coefficient would change because there's a higher velocity. But if there's no fan, we just have one tau. Okay, so this is our mathematical model. And what we're accustomed to is what's called the forward problem. And that's when we're given tau, the time constant of the beer, the air temperature, the time at which we took the beer out of the refrigerator, and the temperature of the refrigerator. And we're asked to predict the evolution of the temperature of the beer from there. So graphically, here's what we would have. So here's time. Here's temperature on this axis, temperature of the beer. Our initial condition is right here. So at time 0, the beer is at 4 degrees C, a typical refrigerator temperature. And the air temperature is TA. So we're also given tau as 5. And what we wish to do is predict the trajectory of the temperature of the beer. And then we would solve this differential equation numerically, or in this case, we could do it analytically by, for example, taking the Laplace transform. And then we will get this green curve. So that's solving the forward problem, predicting how the temperature will behave in the future. And this makes us comfortable because what we're doing is predicting the effect of a cause because we're looking forward in time. And indeed, the initial temperature, you could think of that as causality, looking forward in time. Okay. And here I'm just showing that if you have a little bit of error in your initial measurement, still the trajectory does not change too much. It's not too sensitive to your initial temperature that you measure the beer to be. All right, so the inverse problem is a bit different, and this is what you'll do in your activity. The inverse problem is when you don't know tau, and instead you wish to identify it from data, particularly time series data. This yellow data represents the time series data. So imagine you stuck a thermometer in a beer, and you measured its temperature at different times on its path from its initial temperature to the temperature of the air. And from this data, we wish to identify what tau is. So this is called parameter identification. The way you would do that is pose a loss function here. So this is a loss function. It describes the poorness of fit of the model with a given tau to the data. What you do is you loop over all data, and you look at the difference between what the temperature was at that time. So here, this temperature would be 15. What the temperature was, say this is data point I. And then you compare that to the temperature predicted by the model at that time in the data. And that's going to depend on the tau that you think is the truth, right? So this basically looks at the sum of square differences between the data and the predicted temperature, and you add them all up. And if the model goes right through the data, this will be 0, right? So at best case scenario, the loss is 0, which pretty much never happens. But what we want to do is minimize this loss function. And so we define the optimal tau, or our estimate for tau, to be the tau that minimizes this loss function. So imagine you have a knob and you can tune tau, and you tune it until the curve optimally goes through this data. Okay? That's called parameter identification. And then, so we would get this tau equals 5, which is the green curve that best fits this data here. Okay, and that's what you'll do in your activity. You're going to find tau, not for a glass of beer, but for a thermistor. Now that you've identified tau, it's really powerful because you can look at the trajectory of the temperature of a beer for all sorts of different initial temperatures. And that's what I'm showing in this plot. So the color here denotes a T of T curve for different initial temperatures or refrigerator temperatures. So let's say the refrigerator were around 9 degrees C at first. Then you take the beer out, and this is the trajectory, right? But if it were a bit warmer, the trajectory would look like this. Okay. So once you know tau, you can use the model to predict the trajectory for different initial conditions. And this is just for fun. I want to show you a second class of inverse problem, and it's sort of like a mystery. So now what's missing is the initial temperature, the temperature of the refrigerator. What you have is a piece of data, a single data point. All you've done is you came out in the kitchen, you saw a beer in the counter, you stuck a thermometer in and measured its temperature, right? At time T prime, which is after it's been out of the refrigerator for a while. And let's say the temperature's right here, right? And if you knew that the beer was taken out of the refrigerator at time 0, now the question is, what is the temperature inside the refrigerator? And it's kind of a mystery, right? You want to know what temperature the beer was at time 0, a time in the past. And so now you're inverting causality. You're trying to predict the cause of an effect, which is kind of uncomfortable because, yeah, that's not how physics works. You're trying to find the initial temperature that's consistent with the data that you see. Okay? There's no physical laws for going backwards in time, really. Okay? And so the solution to this inverse problem would be this point here, this purple point, which is estimating initial temperature. So if you could think of going backwards in time. And essentially what you do is you try to find the initial condition that is consistent with your data. Okay? And unlike the forward problem, which wasn't too sensitive to measurement error, now if you have a little bit of measurement error, see, this little error gets amplified to a big error here. Okay? And it's even more severe if the beer has been out of the refrigerator for a long time. Now this little bit of error will be amplified into this very large error here in your predicted initial temperature. And this is known as ill conditioning. And conditioning refers to the sensitivity of a solution to measurement error. So a little bit of measurement in the temperature of the beer will result in a very big error in what you think the initial temperature is. So that's ill conditioning. It's a very important concept for you to think about anytime in the real world, because there's always errors associated with measurements that you take. And inverse problems often are ill-conditioned. Okay. Finally, the last thing I want to talk about is the third class of inverse problem. Now let's say that you came in the kitchen, there's a glass of beer, you measure its temperature at time t prime, and it's 18 degrees, right? And you want to know, one, what is the temperature of the refrigerator? And two, when was the beer taken out of the refrigerator? So both of these are now unknown, T0 and T0. Now this inverse problem actually doesn't have a unique solution. It has infinite solutions. So look, the beer could have been taken out of the refrigerator 5 minutes ago, and the refrigerator is 13 degrees C. So this trajectory here is totally consistent with our data. Or it could have been taken out 8 minutes ago, and the temperature of the refrigerator is a little above 9 degrees C. The data is also consistent with that. So this inverse problem has infinite solutions. None of them are unique. And that's pretty typical of inverse problems. Okay? Okay, so that's my lecture on inverse problems, and now we will actually do some parameter identification in an activity.